Okay, so let's have a look at some properties of behavioral equivalence. I'm not going to spend too much time on this, but we're going to need to use some of these things in proofs and things, so it's useful to have these properties. We've been calling this behavioral equivalence, and equivalence has a formal meaning in mathematics, equivalence relation. So it's basically a relation that's reflexive. In other words, something is always related to itself, which you'd expect for this, right? The program is always going to be equivalent to itself. Symmetric, which means if A is equivalent to B, then B is equivalent to A, and that makes sense in this case too, right? It doesn't matter which way around you consider the equivalence for two bits of program. And transitive, which means if A is equivalent to B and B is equivalent to C, then A is equivalent to C. And again, that makes sense for program equivalence because of the way we think about that. So there's a bunch of theorems here. I'm not going to go through all of them, but you can see that they're proving things like A equiv AA for any A, right? Or symmetry is here. So if A1 is equivalent to A2, then A2 is equivalent to A1. So these are pretty much sort of bookkeeping types of theorems. They're all pretty easy to prove. So we won't spend any time looking at them in detail. You also can get things like, so this is a theorem we saw back earlier, that if and only if is transitive. So it means that you can get the transitivity of command equivalence just straight from the equivalence of if and only if, since command equivalence is just an if and only if property. Okay, so this again, this is one of those things where you define something like these equivalences that we have, but you can't rely on them necessarily having the properties that you really want. So you have to say, okay, I think this is actually an equivalence. So you have to formally prove things. And if you define the relation that you're talking about in a sensible way, then that will be easy to do. Okay, so a bit more interesting is congruences. So what's a congruence? Well, basically, congruences are to do with reasoning about pieces of programs using equivalences. So if you have some big program and inside it you have some expression, say, and you want to replace that expression with another expression that's equivalent to it, can you be sure that doing that replacement hasn't changed the meaning of the overall whole program? Right? Now, if you think about programming, programming experience you have, if you've got a massive Java program and you go to some part of it and you replace some piece with another piece that's exactly equivalent, you're pretty confident that you haven't changed the behavior of some unrelated part of the program or anything. As long as the piece that you're replacing is completely equivalent with the thing that you're replacing it with, everything else should be okay. And that's what congruences are. So a couple of examples here. So if you have, say, two assignments, I becomes A1 and I becomes A1 prime, these can be regarded as equivalent as long as A1 and A prime are equivalent. Right? So in this case, the assignments are the bigger program, and inside the bigger program are these two expressions, A1 and A1 prime, and you're replacing A1 with A1 prime, and you're not changing the meaning of the assignment as long as you replace equivalent things by equivalent things. Okay, and basically you can form congruences for all sorts of different constructs, right? Basically any construct that's got a component in it that's a subconstruct, like it's a command with an expression in it, or it's another expression with an expression in it as a sub-expression, you can always write down these congruence rules. It's a bit tedious to write them all down, but you can write them down. So this is in the inference rule sort of style, but you can write them down in a more formal sense like this. So for example, this is the one that says if those two expressions are equivalent, then embedding those two expressions in an assignment to the same variable, I, yields equivalent commands. Okay, and the proofs are pretty straightforward. So, and they're actually the same proof because this is symmetric. So it's really one proof done in both directions. Okay, so what other sort of congruences might we have? So here's one that says this is a congruence for while loops. So this is saying if you've got one while loop, while B1 do C1, then if you've got an equivalent expression to B1, which is B1 prime, an equivalent command to C1, which is C1 prime, then the while loop is equivalent to B1 prime, C1 prime. So again, this allows things like optimizing a loop by rewriting its body. As long as you rewrite the body in equivalent ways, you haven't changed the meaning of the loop. Again, the proof I'm not going to go through in detail because it's a bit tedious to go through all the details, but I encourage you to have a look. They've got a few more here that are stated, not proven. So for example, if you have a sequence of things, so this is the one that was in the comment earlier in the inference rule form, sequences can be replaced by, as long as you replace the commands by equivalent commands, the sequence has the same meaning. And this is the if congruence that's analogous to the while one that we just looked at. And then once you have those, you can do equivalences of programs with these theorems. So for example, here we've got quite a big long program in this notation anyway. It's an assignment and an if, and then a couple of assignments inside the if. Then we've got the same assignment at the beginning, the same if condition, but we've changed the assignment down in the middle of this if. Okay, so we'd like to be able to show that these two programs as a whole are equivalent, and we're going to rely on the fact that this assignment of y to 0 is equivalent to this assignment of y to x minus x. And the proof is mostly an application of these congruence rules to sort of get down to the position where the key differences are there, and then the simple arithmetic equivalence stuff, mostly using this little theorem here, is enough to get us where we want. So there's a bit of bookkeeping to sort of get you down to that position, but the actual underlying thing is easy. And the congruence rules are giving us, and the things like reflexivity are giving us the ability to sort of just reason about these in a general sort of way. Okay, so I'll stop with that there and pick up in the next part with program transformations.